physics students. Today we're going to be walking you through Chapter 3, Sample Problem D, which is on page 99 in your text. It's about horizontally launched projectiles. Now, in this problem, we're going to be solving for some variables for a projectile, and we probably need to stop and define a projectile. Recall that a projectile is something that's moving in more than one dimension and is under the influence of only gravity. So in this case, we have a rock being kicked off a bridge. It's going to fall, and as you can see from the picture, this path that it's going to follow is going to be a parabolic path. So you can see easily here that the path that this thing is going to take is parabolic, which is something called a trajectory. And the trajectory of any projectile is just the parabolic path that it follows because it's under the influence of only gravity. That means there can be no other forces, no air resistance, no rockets, no propellers, no parachutes. There can be nothing else causing any force on it other than gravity. Only the effect of some downward acceleration of gravity. And it also is a horizontally launched projectile, which tells us that its entire velocity, the initial velocity, is completely horizontal. It has no upward and no downward component to its initial velocity. Okay? So from there, once we understand that we're dealing with a projectile, what we can see is that because it fits the characteristics of a projectile that I just described, that we are going to be able to calculate the missing variables here. And there's a special thing about horizontally launched projectiles that's true. The highest point on its trajectory is called the apogee. The apogee would be the highest point on its parabolic path. Since this is being launched from the highest point, what's always true of horizontally launched projectiles is they always drop from the moment they are launched. They never go upward. Not true for non-horizontally launched projectiles. They always go up a little bit before they do anything else. So our projectile is being launched from its highest point, called the apogee, and is going to fall and move to the right or forward from there. So we're going to tackle this problem just like we would any other problem with the guess method. So the guess method first asks us to list our givens. But projectiles are two-dimensional moving objects. That means that we need to come up with a set of givens that describe what's happening left and right, and a set of givens that describes what's happening up and down. So let's talk about what we can see from what we're given in the question. The Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River. All right, above, that indicates the vertical direction. So we just got some information that our rock is going to drop 320 meters before it hits the river. All right, what else? We're kicking the rock horizontally off the bridge. That tells us that it has an initial velocity that's completely horizontal, and it also tells me that no velocity is directed in the vertical direction. So its initial velocity in the vertical direction, y, is 0 meters per second. What else? We know that the magnitude of the rock's horizontal displacement is 45 meters. So that tells us that it's going to travel a horizontal distance of 45 meters before it hits the water. And our unknown is to find the speed at which the rock was kicked, which we know was entirely in the x direction. Are we missing any important information from our givens? The answer is yes. We know two things about acceleration just from the fact that it's a projectile. If it's a projectile, it's under the influence of gravity and only gravity. Because it's only under the influence of gravity, we know that its acceleration in the y direction, the vertical direction, is going to be g, about negative 10 meters per second squared. And we also know that there can be no other acceleration in the x direction. And these two things are always going to be true of every projectile. They're always going to have no x acceleration and gravity for their y acceleration. Now, once we take a look at that rock to fall will be the same amount of time that it takes for the rock to move horizontally. So when it ends up at the point, when it hits the river, it will have both dropped 320 meters and moved out 45 meters at the same time. And that's the key term. So that means the time that it takes to do its X thing and the time that it takes to do its Y thing are the same. This makes it a lot easier for us to pick equations. When we go to pick our equations, we need an X equation and a Y equation. And the X equation has got to tell us something about the variables that we were given in the X direction. The Y equation has to tell us something about the variables we were given in the Y direction. And we can basically use a kinematic here. It's undergoing constant acceleration, and each component is linear. So that means we need an equation that has displacement, acceleration, initial velocity, and time, but makes no mention of final velocity. That's going to be our no final velocity equation. In the X direction, that's going to look like this. Delta X equals V initial X delta T plus 1/2 A delta T squared. And I'm putting X's on everything because everything in this equation has to describe what's going on in the X direction. The same equation describes what's happening in the Y direction, but I'm changing everything to Y's. Delta Y equals V initial Y delta T Y plus 1/2 A Y delta T Y squared. This is the same equation. They're both no final velocity equations for our projectile. Okay? Now, what can we take from our givens that can help clean this up a little bit? Well, we know that we know that AX is 0. So everything back here is going to be 0 because you multiply all of those things by 0, they're going to get wiped out. We know that V naught Y is 0. So everything in this part of this equation is going to be 0 because it's going to get multiplied by 0. Leaving us with shortened, abbreviated versions of these equations that can be united by the fact that time is the same in both directions. This delta Tx and this delta Ty are the same, which means we can set these two equations equal to each other. What's that going to look like? Well, I'm going to take this first equation for the x, delta x equals V initial x delta t, and I'm going to solve it for time. And since this time is the same as this time, I'm going to substitute it into the other one. So now this one is going to read delta y equals 1/2 AY, and here's where I'm going to move this right in there. Delta x times v, or divided by v initial x squared. Also keep in mind that we know that the acceleration in this direction is g. So from there, we can start plugging in numbers. So I cleaned up my board a little bit here. We want to go ahead and plug in the numbers we were given. So we know that the delta y was negative 321 meters. We know that 1/2 is 0.5. We know that gravity is negative 9.81. We know that delta x is going to be 45. And we know that v initial x is what we're looking for, and that this whole thing is squared. So now we can use our calculator to kind of solve things out here. At this point, it's just algebra. So let's go ahead and finish this off. (45 squared) is 2,025. And 2,025 times negative 4.905 is negative 9,932.63. Using a little algebra trick here, I'm just cross multiplying and moving things around. That means our initial velocity is going to be the square root of that sum. Excuse me, of that quotient. It's going to be the square root of 30.94. So our initial velocity is going to be about 5.56 meters per second at 0 degrees. But don't forget, you've got to give a direction here. Since it was kicked horizontally, you know, it's at 0 degrees. So as we look at this problem, we can see that it's a pretty good example of how all horizontally launched projectiles work. And I got to be honest with you, solving for the initial velocity is probably the hardest thing we could ask you for here. If we were asking you simply to solve for the amount of time it was in the air, how far it fell, how far it landed from the base of the bridge, any of those things would be quite a bit easier than this particular problem. But you can see here that the most important thing to keep in mind is that when dealing with horizontally launched projectiles, that you must break your problem into an x and y set of variables. That way you can come up with an x and y set of equations, which are always going to be united by time, because a projectile will always move in the x direction and the y direction at the same time.